Good afternoon, folks. What I wanted to do is, what I decided to do was, rather than lecturing about radioactivity in class and chewing up some class time, I really wanted to do relativity before the break. So what I'm going to do is I'm going to post this video of radioactivity and nuclear physics. Very simple stuff. If you can add, you can do nuclear physics. There's a little bit of vocabulary and addition, and I'll show you this. Radioactivity in nuclear physics is not normally a big deal on the AP test. It's usually a couple multiple choice questions, very rarely anything more than that. So this is another good candidate like optics to do as a video. And this will allow us to do, again, relativity in class. I have the lights off so you may see glare down here, all that stuff. So again, in your notes, you want to jot down a couple things here, and you can stop the video. I do recommend you stop the video on a couple pictures. I'll talk about them briefly, and you can see if the notes I give you make sense with some of the diagrams. So first of all, we have to agree upon nuclear notation. So in chemistry class, you guys identified a certain element by a symbol, atomic symbol, and they've given X. And then there are numbers associated with each. So for example, this could be carbon, this could be hydrogen, it could be lithium, whatever. And then to identify which element it is, we have the letter showing it, but we also have some numbers. And this nuclear notation is important. So the convention used in physics in most subjects is the lower left-hand corner below the symbol is the atomic number. And you guys probably remember from chemistry, the atomic number is the number of protons. So hydrogen is number one because it's the first element on the periodic table and it has one proton. Helium has two protons, so it's number two in the periodic table. So that's what this number is. Then, in addition to protons in the nucleus of the atom, we also have neutrons. So we normally indicate the neutrons to the right. So protons to the left, neutrons to the right. And then we simply add those two numbers together. And this is the number of nucleons or parts in the nucleus. So again, the typical model of the atom is the protons and neutrons are down the center, and then the electrons are outside. We'll talk about this model in a second. These are the progression of models of the atom. So again, this nuclear notation, protons, neutrons, total nucleons, we simply add those two together to give what we call the atomic weight or atomic mass of the element. Now, a couple of quick examples so you can see that. And I want to talk about isotopes very briefly. I'm going to minimize this. I want to talk about isotopes. So isotopes are the same element, but with different number of neutrons. So hydrogen, for example, has three isotopes. And we talked about this the other day. Hydrogen, the most common form of hydrogen by far is regular hydrogen. And regular hydrogen has one proton. Sorry, I'm making my pen working here. It has one proton. It has no neutrons, and therefore it has a mass of one. So that's regular hydrogen. Hydrogen is just a proton with an electron. That's all it really is. Now, that makes up like 97% of all hydrogen atoms. So if you go in the ocean and take out 50 billion hydrogen atoms, 90-something percent, a huge percentage will be regular, stable hydrogen 101. That's the isotope. There are some versions of hydrogen that have one proton because it has to have one proton, but it's going to be hydrogen. So all versions of hydrogen have one proton. But there's a version of hydrogen has an additional one proton, has one neutron, and therefore it has a mass of two. And there's a version that has two neutrons and has a mass of three. These other two versions, this is called deuterium and this is called tritium. You don't need to know those names. We sometimes call these heavy hydrogen because they're heavier. So when you hear the phrase heavy hydrogen, it just means they have more nucleons, therefore they're heavier. And again, that's not a big deal. Most of the time we talk about hydrogen, has the isotope we're usually talking about is the first one. Carbon is a little bit different. Carbon has a couple of interesting isotopes that are important. So carbon is carbon because it has 6 protons. And then most carbon, as you know, has 6 neutrons, so its mass is 12. That's the basis of the periodic table, and it's the basis of life on Earth. It's carbon-based for the most part. There is a version of carbon that has 2 additional neutrons, so it has a total of 8 neutrons in it, and therefore its total mass is 14. So C14 is a really well-known isotope of carbon that's used in radiometric dating. If you want to date how old some sample of material is, sometimes you use carbon-14 dating. We'll talk about that in a second. It's one of the applications of nuclear physics. The other big isotope that's kind of pops up a lot is uranium. Uranium it's a natural element, but and some of these, by the way, are stable or unstable, and we'll talk about that in a second. So regular hydrogen is very stable. If you have it, it stays there. It won't decay, it won't fall apart. One version of heavy hydrogen, the deuterium, with one proton, one neutron is also stable, but heavy hydrogen, tritium, is unstable. In other words, it falls apart. So it may be produced in an atomic reaction, but it decays and turns back into something else. So we'll talk about those in a minute. Now, uranium has three common isotopes. They're all 92s because, again, they're all uranium. So that first atomic number, 92 protons. But then they have different numbers of neutrons. Now, I'm not going to do the math, but if you add them together, the mass is 234, 235, and 238. Sorry. So these are the isotopes of uranium, and you can do the math to figure out what this would have to be that when they add them together adds up to. I guess that would be 142. And again, I don't really care. That's why I said if you can add, you can figure this out. So the neutrons plus the protons adds up to the mass. Now, these isotopes are all radioactive. And what I mean by radioactive is they spontaneously decay. So if I take a chunk of uranium and put it on the desk in the front of the room, which I'm not going to do, obviously, that uranium is going to fall apart. It's not stable. It can't stay together. So the Earth is hot inside because uranium is inside the center of the Earth, and those atoms fall apart. And in the process of falling apart, uranium will split into parts. It will make up atoms that are smaller. And I'll show you that in a second. And it will give off heat. So one of the reasons why the Earth is hot inside is that there's lots of uranium down inside the core of the Earth, the outer and the inner core, and in the mantle. And that gives off heat and keeps the interior of the Earth warm. It keeps that liquid iron moving around to make the magnetic field. So these isotopes are important. Sometimes they're stable, sometimes they're unstable. Carbon-14 is stable. Carbon-6 is stable. I think 14 is unstable. And all of uranium is unstable. So that's one of the reasons why we get radioactivity. So these things are tied together. And we say they decay. So some isotopes are stable and others will be unstable and undergo what we call decay process. Now, the stability is really based on forces. So if you think about inside an atom, there's some fundamental forces in physics. Gravity pulls things together. Electromagnetic forces can be attractive or repulsive depending on what flavor they are. Remember, gravity is always attractive. Electromagnetism can be attractive or repulsive depending what the charges are. And then there's a nuclear force inside the nucleus. Now, if you think about this, for example, let's go inside the nucleus. Gravity is pulling these things together. And strong force pulls them together. We need a strong force because the static electrical repulsion is pretty strong. So if I have a proton, and the neutrons are shown in gray here, they have no electrostatic because they're neutral. But these protons shown in red, they repel each other. And the nucleus of an atom should fall apart. And physicists realized early on that, hey, if we only have repulsive forces inside between the protons, the atom should fall apart. So they said, hey, we must need some other, they picked a clever name. We need some sort of strong force inside the nucleus to hold them together. And they made up the force called the strong nuclear force. And it's actually there. The strong nuclear force is very, very strong, holds all the nucleons. It actually interacts between protons, neutrons, and each other. So the protons and protons, neutrons and protons, and protons and protons. It's a force between the particles inside the nucleus. And that's enough to overcome the repulsive force of the electromagnetic force. Gravity is relatively weak. It doesn't really contribute much. Now, the reason why that's important, and I give the analogy of if you go to the grocery store and you stack up the oranges, this is a stable geometry. So the geometry, and this force obviously is only with gravity. If you stack oranges this way, they stay this way. And if I stack them on Tuesday, I expect to see them on Friday that way. So some isotopes have a geometry and forces that the nucleon forces are balanced. The position and the relative force between all these nucleons is balanced, so everything stays at rest. So again, hydrogen 1 or hydrogen 2 is very stable. Carbon 6 is very stable. It's got the geometry and the forces all balanced. The problem is when you get to some isotopes like carbon 14 and uranium 238, the geometry is not right and the force is not right to keep this stable for a long time. So some of these isotopes fall apart immediately. You'll literally form an isotope of an atom, and within a trillionth of a second, it falls apart. It's like it's like putting a grapefruit or a watermelon in here. It affects the geometry, therefore the thing becomes unstable. So that's the easy way of thinking about it. Now, in physics, there's a concept known as binding energy, and the only thing I really need you to know is that when you take the parts of the atom and add them together, the total mass of the atom is always less than the parts that make it up. Now, that's a weird concept, so let's write that down. If I take the total mass of the entire atom I would think it would just be the mass of all the parts that make it up. If I take the mass of the proton, the mass of the neutrons, the mass of the electrons, add them all up, I would think the mass would be the same as when they're put together. It turns out that's not the case. The reactants, the stuff going together, always has a greater mass than the products. So what you get out has less mass. So if I take a bunch of protons and neutrons and put them together, what I get is something that's got less mass. And you'll see this with relativity. What happens is that this mass that's missing is actually converted into energy. Now that's a really bad way of saying it, but that's okay. So, and I'll show you an example of that in just a second. So here's the sun. Here's a classic example of Einstein's E equals mc squared, which we'll talk about in class. The sun is made of mostly hydrogen. And so what the sun does is it takes a hydrogen atom, and it takes another hydrogen atom, and it takes another hydrogen atom, and it takes another hydrogen atom. And it adds them all together. And you would think that the total, when I put them all together, would make helium, and then the masses of these two things would be equal. But it's not the case. This hydrogen is 1, 1, 1, 1, 1, 1, 1, 1, and it's a 0 isotope. And so what you get, now you might say, wait a minute, shouldn't it make 4? What it actually makes, it makes helium 2, but the mass is, it has 2 neutrons, and it makes a mass of 4. So there's 1, 2, 3, 4, and there's 4, but it turns out they're not exactly 4. It turns out this is 4.03. If I add the mass of these three together, it's 4.03, and this over here is 4.003. And the numbers themselves don't matter, but you can tell that this over here is less. So what happened? Well, some mass was lost. So it turns out we say plus lost mass. Now again, I'm taking liberties with that phrase. It's really a crappy way of saying it, but for the time being, it helps. So what happens is that, and by the way, this is just four of these. This happens billions of times. So this is times a billion per second. This is happening billions of times per second, where the sun is converting huge quantities of hydrogen into helium. Now the thing in blue is mind-boggling. The sun converts 700 million tons of hydrogen to helium every second. Now that's mind-boggling. That means that when it does that, it turns the hydrogen into helium, but there's lost mass. And it turns out every second we lose a lot of mass. The sun loses 4 million tons of mass every second. Now think about that for a second. If I diet for a week and I lose a pound, I'm psyched. The sun loses 4 million tons of mass every second. And it's been doing that for 5 billion years. So the sun is unbelievably large. It can lose millions of tons every second and still keep on shining for billions of years. So it's massive. And so what happens is that the conversion of hydrogen into helium actually creates lost mass. And that lost mass is turned into energy via the equation E equals mc squared. And this is the lost mass. If I take that and multiply by c, which is the speed of light, it's 3 times 10 to the 8. Well, look at this for just 4 atoms. If I take 4 protons and turn it into helium, I lose a 0.0027. I think I'm doing the math right, but you get the idea. Whatever that is. It's a tiny mass. If I take that tiny mass and multiply the big number squared, I get a lot of energy. So that's kind of the point. This is what Einstein found, kind of, I won't say by accident, but he did the math and said, hey, look at this. This is an interesting phenomenon. I wonder if this is true in the real world. And that explained how a star actually converts hydrogen to helium and how it shines. It's not burning. The star's not on fire. The sun makes way more energy than if you burned it. If I burn a log, I get a couple million joules of energy. If I fuse the log, if I do the process we're talking about here, I get 50 bazillion times more energy. So this is the golden, where physicists are trying to figure out how to do fusion on Earth, because the byproduct is helium. The byproduct's nice. You get 2 things out good. You get helium, make balloons, and you get lots of heat and mass and energy. So people are trying to figure out how to do fusion in the laboratory. Okay, so again, this is why this nuclear and radioactive part is kind of important. Now, again, Einstein used E equals mc squared. We'll get into this when we get to relativity and into quantum. There's some really interesting, I used the phrase masses converted to energy. That's really a bad way of saying it, but we'll come back and fix that later. Okay. Now, you do not need to do detailed calculations. UConn occasionally sends a question where the kids actually have to get in and actually calculate the amount of energy and this notation. So ignore this page. We're not going to do that this year. If you take a course in nuclear physics, you'll do this. And it's not difficult. It's just a lot of conversions. So don't worry about this. I did this for UConn. Now, the thing that's interesting about radioactivity, Einstein did not like it. Einstein was a classical physicist who liked things to be orderly. And radioactivity is one of these things that's kind of like quantum, where matter behaves strangely in an uncomfortable way. So it's really a quantum effect. And Einstein, although Einstein was fundamental in developing quantum mechanics, he didn't like it. So Einstein liked things that are very predictable. So if he thinks about an isotope, so I said some isotopes are unstable and they decay. The phrase we give is decay. Decay just means they fall apart. I said spontaneously transmute. So they'll spontaneously change from one atom to another. So for example, if I take, and I'll show you a couple examples of these, but if I take some uranium and it's 238, and this might be the example on the next page, 92, 238. If I wait long enough, that uranium just falls apart, turns into lead, and it turns into some other stuff. So it just falls apart. I forget the number for lead, but I'll show you the math on this. So you're sitting with a pile of uranium on your desk, and it just falls apart naturally. It decays spontaneously. We can't speed it up by hitting it with a hammer or heating it. It just does it on its own. But Einstein didn't like that because not all the atoms do the exact same thing. If I have two uranium-238 atoms sitting there, one of them will spontaneously decay 1 minute, and the other one will take like a week longer to do it. And the fact that it doesn't happen, the fact that every atom doesn't do the exact same thing the exact same way, kind of drove Einstein crazy, and a lot of people crazy. It really shows you the quantum nature of matter, which we'll get into again in more detail. Now, there are 3 or 4 types of radioactive decay I'd like to talk about. And these are relatively simple. They're just vocabulary. You got to memorize what they mean. So the first one's called alpha decay. And alpha decay is just addition. It's just a fancy way of saying 2 protons and 2 neutrons fall out of the nucleus. Now, I mentioned this before. It's actually called an alpha particle. That's why we call it alpha decay. So an alpha particle it's usually symbolized as alpha, and it's 2, 2, 4. Some books write it as alpha, the fish symbol, the Greek letter alpha, or you could write it as helium. You could say it's helium 2, 2, 4, because remember, 2 tells you what element it is, and so it's got to be helium. Now, it turns out because it's 2 protons and the electrons are ripped off, it's usually ionized. It's usually plus plus, but that's not important. An alpha particle is just 2 protons and 2 neutrons. You can write it as alpha, you can write it as helium. It's a helium nucleus. Now, this is where the math comes along. This element over here on the left is polonium. It's got atomic number 84, and it's got a mass of 214. And I can probably do the math here and figure out this must be 130. I think I did that right. My brain is on hold. So it's got 84 protons, it's got 130 neutrons, and it's got a total mass of 214. Well, this polonium is going to be called the mother because the mother will form a daughter. It's going to turn into another particle as the alpha particle is ejected. So this polonium sitting here minding its own business, and suddenly it's unstable. It throws out 2 protons and 2 neutrons, and it turns into something else. Well, what's it turn into? Well, I don't know. Let's do the math. Well, it had 84. It gave up 2, so it must have 82 protons left. It had 130 neutrons. It gave up 2 neutrons. It must have 128 neutrons left. And therefore, the atomic weight of this whole thing must be 210. And what is that stuff? Well, I grab a periodic table, I look it up, and it turns out it's lead. So polonium is an unstable isotope. This isotope, 214, polonium-214, is unstable. It falls apart on its own. You don't do anything to it. You just let it sit there. In fact, there's nothing you can do to make it fall apart sooner. It sits there and it falls apart. It turns into lead-210, and that's because it gave up an alpha particle. So the AP typically says, they'll have a question, will say, polonium, this isotope polonium undergoes alpha decay. What's the daughter product? And if you can add 82 and 2 to get 84, you're good. They don't expect you to memorize the periodic table. They'll give you probably some choices, and the choices, only one of them will add up all the nucleons, the charge, and the mass. They all have to add up. You can't have more protons on one side than on the other. It's just like balancing equations in chemistry. We're doing the exact same thing. So this is called alpha decay. Alpha decay is the most complicated. It's really 2 protons, 2 neutrons. You just didn't memorize that. and be able to add. Now, another type of decay is called beta decay, and beta is just the fancy name for electron. Now, there turns out there are two types of beta decay. There's beta negative and beta positive. 99% of the time, the beta decay is negative. So usually when the AP says beta, they mean electron. Now, this is kind of weird, so you might want to stop the video and write this down and listen closely. Let's take carbon-14. It turns out carbon-14 is unstable. This is the isotope of carbon. It has 6 protons, 8 neutrons, and 14 total mass. Carbon is going to give up an electron, but the electron is not coming from the outer levels. Like you've been taught in chemistry, we have electrons orbiting around the nucleus up in the clouds. It turns out the electron actually comes from the nucleus. Huh? Well, let's go down here. Let's look down here. What happens is that if you think about a neutron is 0 protons, 1 neutron, and a mass of 1. So this symbol down here for the neutron is 0, 1, 1. The neutron, and I'm not sure if anybody ever told you this, but a neutron is really just, it's neutral. It's really just a proton and an electron. So think about it. This neutron is going to fall apart and eject an electron. That's the beta particle. This is the beta minus. Okay? But in the process of that, the neutron has turned into a proton. So this makes sense if you think about it. This is neutral, this is positive, this is negative. So what's really happening is that when you have carbon-14, it's going to take one of these neutrons, 8, and turn it into 7. But in the process of doing that, it's going to kick out an electron and convert one of the neutrons gets turned into a proton. So this neutron, this 8 goes down to 7, but this lost neutron now turns back into a proton. So this will go back up to 7. So it basically turns a neutron into a proton and gives over an electron. So that's what this, and it's a little confusing, but that's what this is showing you. I have the same number of protons, neutrons, electrons on this side as on this side. Now, the electron symbolizes the E with a little negative symbol. This thing right here is called a neutrino, and you don't need to know about neutrinos. Neutrinos are particles that will, it's not mass conservation, but it's conservation of kinetic energy and some other stuff. So it's a little symbol. It's like a V with an attitude, and that's called a neutrino. And it's there to conserve momentum and kinetic energy. So the basic idea behind beta decay is an atom is going to take one of its neutrons and turn it into a proton. And so carbon literally turns into nitrogen. So you put a pile of carbon on your desk and you wait a little while and it turns itself into nitrogen. And again, Einstein didn't really like that. That's called beta negative decay. Okay? Now, there is a beta positive decay that for your year is pretty rare. They don't usually ask about this. It's the opposite position. So we're going to start with oxygen that has an isotope of 8 is the number of protons. That's what makes it oxygen. It has 7 neutrons. But in this case, it's going to take a proton, turn it into a neutron, and produce a particle called the positron. Now, a positron is a positive electron. It's not a proton. It's a positive electron. So we symbolize it as an electron, but we show it being positive. So it has, if I take a proton, again, protons are positive, neutrons are neutral, and a positron is positive. So the charge is conserved. And one of my protons, 8, disappears, but now I've created a neutron, so my 7 goes up to 8. So this is a beta positive. It's giving out a positron, and it also has a neutrino. And again, the element has transmuted. So oxygen literally disappears, and nitrogen shows up, and a positron comes out. So it's just this is really just vocabulary to memorize. So the AP rarely asks about this in much detail. 99% of the time, it's alpha. If it's not alpha, it's beta negative. But I know I saw the revision for the new AP Physics 2 coming in 2025, and they said they're going to talk about beta positive, so I thought I'd just mention it. So the two forms of radioactive decay are alpha particle decay and beta particle decay, and beta has 2 versions, positive and negative. Negative, much more common. Now, there's a third type called gamma decay, and we're not going to get into this. This gets pretty complicated. You have an element that's excited, and it becomes unexcited by giving out a gamma particle. These gamma particles are really dangerous. These are the ones that are super high energy. They interact with your DNA. The sun does this a lot. It has excited atoms that kick out a gamma particle, and it goes back to being stable element. And again, this is pretty complicated. Well, we might mention this a little bit later, but gamma is dangerous, very dangerous. This is what they use for radiation, for chemotherapy. They'll do gamma particles, usually. Now, here's a great picture. This is a picture that shows up on every assessment I've ever seen. So what they're showing you is stuff we've all seen before. Here's a radioactive source. It's some radioactive material. It's going to kick out particles. It's going to go alpha decay, beta decay, and gamma decay. And you may recognize the symbols here for these X's. They represent a magnetic field going into the paper. So these particles are traveling through this magnetic field. And check your right-hand rule, see if this makes sense. Well, the particles are moving in this direction. So here's my velocity vector. And the B field's going into the paper. So I'd have my thumb pointing in the direction the particles are moving. I have my fingers on my right hand pointing into the paper. And because alphas are positive, they're going to be deflected to the left the way my palm is pointing. Beta is negative. They're assuming this is beta negative. They didn't say it, but like I said, 99% of the time, the beta is the negative version. So that's showing the particle bending to the right because that's negative knuckles. And the gamma particle, which is uncharged, goes straight. Now, the curvature depends upon the charge. This thing's +2, so you might think it will bend a lot. And this is -1, so you might think it will bend a little. But the mass of the alpha particle is huge. It's 2 protons and 2 neutrons. So it's got a huge mass. And this guy's mass is just an electron. So its mass is tiny. So the amount of curvature depends upon what the charge is. And although this has twice the charge, alpha has twice the charge as the beta, the alpha has, it's like 10,000 times the mass. It's got 4 nucleons, and this one has none. So the mass of this particle is huge. So it's like a truck going around a corner. It's harder to turn. This particle turns really quickly. So this picture shows up on almost every standardized test I've ever seen, and it should make sense using the right-hand rule. So this is radioactive, and this is how we found radioactive decay. They take an element, and they notice that, hey, this particle falls apart, and they could look at the particles, how they're deflected by magnetic fields, and figure, oh, they must be positive and negative and neutral. So it's a good application. Now, here's another picture that I think might be worth pausing and watching for a second. We're going to take the isotope uranium-238. They didn't bother putting the 92 on there because it's uranium's all 92. Here's the isotope of uranium-238. And again, this is something that drove Einstein crazy. Uranium-238 decays, and it undergoes an alpha decay. You can look this up in a book somewhere. You don't have to memorize this. So if I have uranium-238, it's unstable. The geometry and the forces aren't balanced. And it turns out that it gives off an alpha particle. Well, alpha particle means it lost 4 nucleons. So it has to, on this chart, we have protons and we have nucleons, or neutrons. And so it drops from 238 down to 234. So it's going to have, instead of having 92 protons, it only has 90. And instead of having 146 neutrons, it only has 144. So the total adds up to 234 versus 238. So that's what uranium-238 does. It kicks an alpha particle. Then when it gets down to thorium, remember, it's changed its number of protons, so it's now switched from uranium to thorium. Well, thorium itself is unstable. Most of these elements that are really heavy, high on the periodic table, are unstable. Above, I forget what number it is. When you get above like 80-something, they're all unstable. They don't hold together. And all of them are unstable above that number. Some of them are stable below. So if I have thorium-234, and its atomic number is 90, well, that undergoes a beta decay. So it actually turns one of its neutrons into a proton. So its atomic number goes up, but it lost mass in the process, so it drops down. So it's gaining protons because it's losing neutrons. They're being converted by beta negative decay. And again, that's pretty complicated. Now we end up with uranium decaying to thorium down to whatever this is, down to uranium-234. 234 decays by alpha, down to a different version of thorium. That decays down to 226 radium. That decays down to 222 radon. That decays down to 218 polonium. And this is where Einstein really got bothered. Some polonium undergoes alpha decay to lead. Some does an intermediate step down to actinium, or whatever the heck this is. It decays by beta decay, and then it goes alpha decay. So it turns out this will decay down to some intermediate thing, but it does it 2 different ways. And Einstein's like, hey, they should all do the exact same thing. It's like the atoms know, okay, you decay this way, I'll decay that way, and I'll meet you down here. So eventually what happens is this 238 will decay a whole bunch of ways. It's turning into different elements all the way along here. And eventually it gets down to lead-206. And it turns out lead-82-206 is stable. It will not decay. So uranium will eventually arrive down here at this point. Now, It's going to take some time to do this, and we'll talk about that next. And you don't need to know the details of this. You just need to understand, hey, there's there's alpha decay, and there's beta decay, and there's alpha, 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 beta, 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 alpha, beta. It's just decaying different ways. And this theory that people came up with explains really nicely why we have these isotopes. So this model of atomic decay makes sense. It works. These are controlled by another force. Which way they decay is controlled by something called the weak nuclear force, and that's way too complicated to get into here. Okay. Now, it turns out the thing I was talking about was how long does it take to do it? It's called half-life. So half-life is literally defined as how long it takes for half the atoms to decay. So I take U-238, I set it on the table, I wait a little while. Some decay immediately, some decay later, some even later. Newton and what he called hated that. But what happens is over time, there's a very consistent time for each isotope to decay down to half its atoms. So if I take some uranium-238 and put it on a table and just wait, after a certain number of years or days or weeks or hours, half of it will have decayed and half will still be there. Now, the best way to look at that is by a graph. So this is the easy way of doing it. So we're going to start with don't worry about these labels. We're going to start with a whole unit, like 100% of some atom. And I'm going to wait some time, and in some period of time, half of these will have decayed. And that time period is called the half-life. So if I wait long enough, one half-life, half the atoms are gone. If I wait another half-life, it's the exact same amount of time, half of those are gone. So I went from, let's say there's 100 atoms. After a certain amount of time, I have 50 atoms. After that same amount of time, I have 25 atoms. After the same amount of time, again, I have 12.5 atoms. They're going to decay at a rate. Now, this is exponential decay. Now, in math class, you learned how to do this, exponential decays. You can do it that way if you want to, but it's a lot easier to just look at half-lives. So after one half-life, I have half the atoms remaining. After two half-lives, I have a quarter of them remaining. After three half-lives, I have an eighth of them remaining. In other words, the number of atoms gets cut in half every half-life. And this is really good for approximation. It's much easier to do it this way than the math way, but both work. This is a good approximation. The AP is always going to give you numbers that are easy to approximate. I'll show you an example of that. So you could do it this way. I'm not teaching it this way. UConn usually makes me do it that way, not this year. The easier way is just looking at half-life. Now, a really good example of this, and it's a little controversial, but it's kind of applicable regardless of your religious beliefs. But we're coming up on Easter here, and obviously the big event of Easter is the resurrection of Jesus from the dead. So carbon-14, it turns out that when Jesus was buried, if you believe in this version of history, when Jesus was buried, he was wrapped in a cloth. It's called the Shroud of Turin. He was wrapped in a burial cloth, which was a tradition 2,000 years ago. So the body would be wrapped up in his linens and placed into a tomb, and then that was it. Well, it turned out that I think it was in the 12th century or something, they found a piece of linen that had this eerie image of a human being on it. It's literally a cloth that was wrapped on a person. So the body, it actually you could see the muscles and the bones and the face, and here's a zoomed in picture of this burial cloth. And this was supposed to be found in Turin, Italy, and it was supposed to be the burial cloth of Jesus. So this eerie image of a human face shows up on this cloth. And people said, well, this is the burial cloth of Jesus, and here's proof that Jesus was raised from the dead. His body wasn't there, but we found the cloth. And they started to do analysis, and this gets pretty off the topic, but they tried to figure out how this image formed, and scientists were brought in saying, is it a form of photography? Was it painted on here? They really couldn't figure out how the image was formed on the cloth. And so they said, well, let's see how old it is. Let's see if this thing can be old enough to be 2,000 years old. So what they did is they took carbon-14. Now, carbon-14 is a natural isotope of carbon that's in your body when you're alive. So right now, your body has a bunch of carbon-12 and a bunch of carbon-14. If you're alive, the ratio of carbon-14 to carbon-12 is fixed. So in your body, you have a certain ratio of carbon-12 to carbon-14. And as long as you're breathing, that ratio stays about the same. But when you die, the carbon-12 is stable, so that stays there, but the carbon-14 is not stable, so it falls apart. So the longer you wait, the more the carbon-14 disappears and the more carbon-12 you have. So the idea is that carbon-14 has a half-life. Half the atoms will decay in about 5,700 years. So when you're alive, the ratio of C12 to C14 is fixed, and when you die, the C12 and C14 ratio changes, and so they can look at the half-life of the C14 in your body and see how much C14 is left after you died. And so, and this is complicated, but basically what they did is they did a test on the Shroud of Turin, and they found out now that there's a huge controversy about this, as you might suspect. But some scientific research, they took tiny little fragments of the shroud and they subjected to carbon-14 dating, and they got the age of the shroud to be about 1000 BC. Sorry, AD, obviously AD. So 1000. So much too late. People are saying, "Oh, this thing doesn't age. It doesn't meet from the time that Jesus was alive, so there's no way it could be his burial cloth." The carbon-14 dating suggests that was made or produced about 1,000 years ago. Now, there's a lot of controversy about that because there's impurities, there's pollen on it, and the pollen could be older. But it's interesting. It's something that's an interesting application of history of carbon dating. Now, carbon dating has a limit. If you think about this, the number of atoms gets cut in half every about 6,000 years. So you start with a bunch of atoms, 6,000 years later it gets cut in half, 6,000 more years gets cut in half, 6,000 more years gets cut in half. So you're not going to use carbon-14 dating for dating a dinosaur. Dinosaurs are millions of years old, so the number of half-lives of that the atoms would have to go through in carbon dating for a dinosaur would be thousands of half-lives. So there'd be almost no carbon-14 left. So there's a limit to how much you can do. And again, they use this for sampling bones. Bones, things that are alive, relatively recent, you can use carbon-14 dating relatively quickly to figure out how old something is. And it's good up to about 20 or 30,000 years. But once you get down to millions of years, the original carbon-14 is reduced down to 0.000001%. So carbon-14 has a limit to how you can date things. So again, it's real simple. If I give you 1,000 grams of some isotope that had a half-life of 276 days, and they ask you how much is remaining after a certain amount of time, you go, okay, there's one half-life, there's two, there's three. The AP almost always makes it 3 half-lives. If you see this, 276 days is it's a little less than a year. So after 3 years, it's gone through maybe 4 or 5 half-lives. So you just go to the chart and say 1 half-life, 2 half-lives, 3 half-lives, 4 half-lives. Oh, we only have 12% left. You can approximate. So again, some atoms are unstable. They fall apart. And when they fall apart, they have a certain time period they take to fall apart, and they have a certain type of process when they fall apart: alpha, beta, and half-life. So this is a big thing. Now in class, I normally show some samples. We have some safe alpha, beta, and gamma radioactive samples, and we'll talk about it a little bit in class if I have some time. But I wanted to show you this video because this allows me to cover radioactivity in 20, 25 minutes versus doing it in class and showing it in class. Now I'd rather talk about special relativity. We'll talk about some of this other stuff. We use radioactivity to actually look inside atoms, and we talk about fusion and fission. This is not something you need to know. Fission just means break the atom apart, and fusion means put them together. This is how the sun works. This is how nuclear bombs work. So we're not going to get into this in any detail. Okay. We'll talk about some of the stuff in the quantum unit. Okay, so I just wanted to give you a quick introduction to radioactivity. I'm going to say cancel that. I'm going to stop the video, and again, if you have any questions in class, ask. But I'm going to try to speed things up a little bit and get to relativity before the April break. All right, hopefully that recorded, and I'll post this soon. Thank you very much. Bye-bye.